mean, I assess the feedback are
Right. It's good you guys are here today because we have a pop-up quiz. Very simple, only 2 questions. At the end of the lecture, just let you know at the very beginning so you are paying attention to it. You hate me? Why he did that, he never told us. Very simple questions, only 2 questions. I'm going to cover that for the whole lecture. There's no excuse for not knowing how to do it. You did the same thing in the lab, but we are a little behind on the timer stuff, and I can tell from your eyes, a lot of people are still getting confused how to calculate the time, the counts, okay? So we're going through all the problems posted by Dr. Carlson on his website, every single one. They are just different numbers, but exactly the same questions. And basically, like 10 to 15 questions, but only 2 types of question. I think I taught that a little bit for Lab 1 and Lab 2. The TA was not teaching that. I was trying to do it for Lab 3 and Lab Section 3 and C and D. But I saw the TA was doing really well for Section C. The 2 guys are teaching really well. And Section D was too late, but I saw people, they were teaching. So hopefully you learn something from him. But I will repeat everything in the lecture, so make sure everyone has 0 problems with these 2 types of questions. Okay? That's the goal. First, look at the schedule for the exams. I just posted yesterday, I think. The first midterm on the 27th of September. It's an in-class exam, 15 minutes. And the questions are very similar to the ones in the homework assignments. Yeah, nothing will be beyond that. Or the labs, or the questions in the labs. And I'll do a review before the exam, for sure. And there's another midterm exam on the 1st of November. And there's the final exam on the 2nd of December. And these are not common exams. If you received something from the testing center regarding the common exam stuff, I didn't know they just send it to all the people because I was trying to copy one from Circuit 1, which is the common exam, and directly forward it to everyone. I haven't modified it yet. I just copied. So common exams are not happening in this class. All the 3 exams are in-class exams, even though they are shorter. This is a hands-on class. I don't want to make it very theoretical flavor. I give you all the calculations on the paper, but still you cannot, after you can do all the calculations, you can still not get a job. That's not the goal of this class. This is a super hands-on, practical class. So exams just testing your fundamental knowledge about the timers and interrupts, logic, things like that, right? So they're very short, 15 minutes on the paper. Oh, actually, 4th, not 2nd, 4th of December for the final, okay? Does this work for you? Any questions? You need a longer exam? You want more questions on the exam? No? Okay, let's go through the calculations. Let me draw on the paper first before we come to the text. I already talked about this for the section A and B, but C and D didn't hear this. So there are 2 registers for the timer. Timer 0, timer 1. I think it has 5 timers on the chip. It's a lot of timers. So we have used the timer 1, but I think for lab 3 we're going to use timer 0 as well. I'm going to show you why we have to use timer 0 to create a little delay in between different notes, the music notes. So for timer 1, for example, has a high, has a low, right? Every single one is 8 bits. It's an 8-bit register. So if you have 8-bit, it's going to be 8. So totally 16, right? So it's going to be 0, 0. If you count from 0, 0, 0, 0, because every single hex digit represents 4 binary bits. So 0 here is 4 zeros, right? It's 4 zeros, 4 zeros. So total is 16 zeros. If you count from 16 zeros to 16 ones, how many counts do you have in total? 2 to the 16th. No, I'm counting 0 as well. So starting from 0 to whatever this number is, you'll have totally 2 to the 16th number in there. So which means 2 to the 16th counts. And this, assuming it's a 1-to-1 prescaler, I'm going to explain that. What is that? Prescaler. And why do we need it? So if I'm telling you it's a 1-to-1 prescaler, which means I'm not dividing the frequency, you can design a frequency divider for generating all different frequencies using PLL or other technologies. But we just, or counters, right? So we are not touching that bottom level of digital design. We just need to use it. Embedded system designers, we just know how to use it. That's good enough. So 1-to-1 prescaler, which means we are doing that 60 megahertz crystal frequency for the chip, and we're not dividing it. It's 1-to-1. So if you have like 1-to-2 prescaler, for example, and the main frequency for the chip will become 8 megahertz instead of 16. So on and so forth, right? If you have 1 versus like 256, you'll use this for timer 0. And that frequency will become 60 megahertz divided by 256. Slower or faster with this type of prescaler. It slows the crystal or the main clock down, right?
Can you have like a 2-to-1 prescaler?
Oh, you scaled it up, right? It's just doubling that frequency.
Yeah.
I don't think the chip has that functionality there, but some of the chips can, depending on the application. But usually we have the fastest frequency as the main clock, and then you divide it. That's easier in terms of the digital design. You can use counters. So counters, like when you count, for example, you have a very fast frequency here, right, as original clock, and you count for like 2, then you toggle it, which means you count for like 1, 2, you toggle it. Count for 1, 2, you toggle it. So you can divide the frequency, you can slow it down easily, use a counter. Okay? But making it faster, sometimes you just couldn't, depending on the technology of the chip. Sometimes the chips, the transistors are being designed in a certain technology. For example, the 40-year-old ones, 500 nano. So which means the length of the transistor is like 500 nanometers as a minimum. So these huge transistors will introduce a lot of parasitic capacitance. So if you have learned circuits, you know caps, it takes time to charge up the caps. It's like a bucket, you want to fill it up with water, right? It takes time. If you have a huge bucket, you use a little pipe to fill it up, it takes time. So the caps are actually holders holding all the charges. The charges are, you can imagine they are just waters in the bucket. Okay? If you fill it up, use a big pipe and just filling up a little mug, you can do it really quickly, no problem. Either pumping water out from the mug or fill it up with a huge pipe of water going to the mug. So what about you fill up the ocean with a little pipe? It takes forever. You'll never charge it up, right? Same thing as you pump water out. It's actually charging and discharging the cap. Same thing like filling with water or pumping water out from the bucket. So in that case, you couldn't run it really fast. So we usually have a fastest frequency at the main clock, then we divide it. Okay. So for here, if we have a prescaler like that, we are dividing the frequency by this factor, so it slows it down. So why do we need a prescaler though? What are the applications?
So you don't overflow so fast?
Yeah, that's right. If you have a super fast frequency and you only have 16 bits, and this number is what, like a 60,000 or something? I forgot. I couldn't remember. We can calculate it. So know the number, what the number is. 2 to the 16th, right? Only 65,000. Not too big, actually. So for something can count for 16 megatimes per second, you can overflow very quickly. And how long it takes to overflow? That's question 1 on the quiz. how long it takes to overflow it. Do you know the it's so 60 megahertz means it's 60 mega counts per second, right?
So 1 second.
How many counts do you have? 2 to the 16th counts. That's from 0 to 2 to the 16th, right? This is how many counts do you have?
It'll overflow 24 times in a second.
Oh, the frequency?
So
It's about it's about that. Yeah, it's 1/4 something milliseconds, right?
Yeah, I found how many times it would overflow in a second.
That's right. 24.4 cycles actually. But let's get to that point later. Let's figure this out first. But I'm not asking like how many overflows per second. I'm asking how long it takes to overflow once.
0.041 seconds.
Yeah, but how we calculate it?
Would it be you divide two
That's right. Yeah.
counts by 16?
Yeah. So it's gonna be if you look at the units, right? I'm asking for how long. So the unit will be what? Seconds, right? Did you see seconds here? Yes, it's over here. So I want to flip it to the top, right?
Yeah.
So how to flip it? This number divided by this, and you got to counts to the bottom so you can cancel it. Okay, so it becomes 2 to the 16th counts over 16 mega, right? Counts. Seconds will be flipped to the top, and then this is cancel. So this number will give you how long it takes, and eventually this is a 4 point something what? 4 point what?
0.001.
Oh, I mean milliseconds wise.
Oh, in milliseconds.
4 point what? 4.1?
4.096.
096, right? So only takes 4.096 milliseconds to overflow this 16 bits register. So now, if I'm asking you another question, how long it takes to finish 200 counts? How long? How long means time. How long it takes to finish 200 counts? Same thing, right? Just 200 divided by?
16.
Yeah.
12.5 microseconds.
Cool.
So yeah, you take 200 counts divided by 16 mega. And you
Exactly.
Get, 12.5 microseconds.
Say it again.
12.5 micro.
Microsecond. Thank you. If I'm asking like one count, how long it takes? It's 1 over 16 mega. 10 counts, 10 over 16 mega. 100 counts, 100 over 16 mega. This is question number 1. Is that clear? Is that clear, everybody over there? 6th grade math. You can also use Dr. Carlson's division equations for long ones. You are more comfortable with that. But I prefer this. It's super simple. Question number 1, super simple. Give you a count, calculate for a time. Right? Any questions? No? What's that?
Do you want to use a calculator on this test? On this pop quiz?
Yes.
Awesome.
So if you have a 1 to 2 prescaler, you just do your frequency divided by 2, and then that's
Yeah,
what you're doing?
let's do it. 1 to 2 prescaler. Let's say 2 to the 16th counts, right? Divided by 16 mega. Divided by 2. Right? Counts per second. So counts second will be flipped to the top. You have prescaler 1 to 2. This is how you find out the time. How long it takes by using this clock instead of the original clock. Okay. So you are given with the count, calculate for the time. You are given with the time, can you calculate the counts? So after 2 milliseconds, how many counts has been done?
Are we still using the 1 to 2 prescaler or just the 1 to 1?
Just 1 to 1.
1 to 1.
Yeah, 2 milliseconds is the time, right? And you need to know the counts. And because the original clock is 16 mega counts per second,
Would it be 32,000 counts?
you can calculate 2 times 16 will be 32. Mega cancel by 10 to the negative third, right? So we're getting K here. How we do it? Another way to do that is if you directly want to cancel that unit, second, the time, you can convert this one to second by divided by 1,000. So this becomes second, right? This becomes second. So you can directly cancel second. So this will give you the number of counts. Any questions on this? No? Clear? Okay, let's take a look at some examples. So these are all the questions from Dr. Carlson's website. I didn't recreate them, but I found out some of the solutions are wrong. So I want to let you guys know what are they. First one. Let's look at this question. We have done that already, right? This many counts per second, and this many counts to overflow. It takes 4.1 milliseconds to overflow. And it's a very critical number to know, because sometimes it's asking you for, you'll see the number, you'll see the problem. Yeah, it's difficult to describe, but you'll see it in a bit. So every 1 millisecond has how many counts? Yeah, it's a time is given, right? Ask her for the counts. Easy, because it's 16 mega counts per second, so you'll know that second will be canceled. You directly use that time times that counts to find out the number of counts during that time frame. Another thing you need to know, every count takes 1 over that frequency, right? Every count takes 1 over that frequency. So every count is actually 62.5 nanosecond. Okay, question number 1. How much time goes by in 30,000 counts? Which divided by which? Which times which?
The amount, how long a count takes times 30,000. So the 62.5 nano times 30,000.
Yeah, but also, let's just type over here. I know that's correct, but let's follow the equation I wrote on the paper, okay? So everyone can follow. It can be 30,000 divided by 16 mega, right? Okay? That's just one of the 2 questions. Given a count, ask for the time. So starting at this, how long will it take for timer 0 to roll over? So we are assuming a 1-to-1 prescaler. So starting at a number, how long it takes to roll over or overflow that timer? How do we tackle this problem? This type of problem?
We just take 2 to the 16 minus 30,000.
Yeah, exactly. Because that 30K is the offside over there, right? Serving as a starting number. So what's happening is for that TMR0 register, timer 0 register, it already has 30K in there. Okay, so it's gonna start from here until here. So this is this number is 0xf, and the total number, let's just assume, is 2 to the 16th. Okay, even though there's a 1 difference, but let's just assume it's 2 to the 16th. So this number minus 30K will be this number, will be the number of counts. It's asking you how long it takes to finish that number of counts. So this number do what? This is count. This is the count, right? Sorry. This is the count. we need a time. Divided by or times 60 mega.
Divided by.
Okay? Next. What starting value would result in timer 0 rolling over in 3 milliseconds? You have to pay some special attention to it because sometimes you have to consider that overflow because it's 3 milliseconds is less than 4.1 because still within one cycle. What if I tell you it's probably not making a difference here, but anyway, just look at this problem. So what's the starting value will result in timer 0 to roll over in 3 milliseconds? So how long it takes to finish the whole thing? 4.1 millisecond, right? So it's asking you what's the starting value, like you want to put in here. So for the rest of them, only takes 3 milliseconds, right? So how to get this one? Do you want to directly use 4.1 minus 3? It's an estimate, right? You want to use a more accurate value. So how do you get 4.1? It was 2 to the 16th divided by 16 mega, right? Yeah, use this number instead of this. It's more accurate. So this is something like 4.1 something, okay? 4.09, right? And this one minus 3 milliseconds will give you the time here, right? That's the time. And you know the time, can you calculate for the counts? Number of counts. Divided by 60 mega? Times 60 mega, right? Why? Because it's 60 mega per second. You times it, you can cancel second. If you divide by it, you flip second to the top. So now you have second here already. You want to times 60 mega per second, so second get canceled, right? Okay. Is that clear? Let's move to the next. I already provided the solution here, so but let's take a look at it. In the algorithm below here, okay? What initial value for TMR0 would produce a 2 millisecond pulse? Keep in mind, what is a 2 millisecond pulse?
For 2 milliseconds.
Yeah, 2 millisecond pulse is this, right? So what's happening is you are actually take a look. So this one you clear the interrupt. This is another thing I want to talk about. Let's do this first. So it's confusing you, it's scaring you. So once it overflows, the register I talk about, once it overflows, it's going to turn on a flag. Just to let you guys know, one of the bits in one register will be turned on. So I have to manually clear it, so you can start the next timer, right? Start up the timer again. So if you look at this one, sometimes it's confusing. We come back to the main code here. Okay, this is. Not this one. Here. Right, it's something I want to talk about in a bit. That's for lab 3. It's an example code. So I'm asking you to fill up the space for your with your code so you can finish lab 3. Okay, something also important. But let's look at this first because I have 2 registers in the same code at the same time. You may have a question, a big question mark in your mind. So they look similar here, right? TMR, timer 0, IF, interrupt flag. Timer 1, interrupt flag. Only difference is timer 0 is timer 1, right? But why the register's name is different? Why this is like interrupt control? Why is peripheral interrupt register? Why does it have a different name?
Because timer 1 is the internal timer.
They're both internal timer.
Oh,
They just placed these interrupt flag in different registers.
gotcha.
Okay? Don't dig too deep into it. The digital designer who knows how to program Verilog, design it. What's the company?
Microchip?
Yeah. All right. So if you want to know if this is true, let's visit what? The data sheet. Data sheet. I printed out. This is my personal printer. Why do I have to say that? You want to see a page looks like this, right? Because it shows the nice table, shows all the bits in that register. PIR1, that's the register you have in the code. PIR1, peripheral interrupt request flag register, okay? And you are looking at the bit. Here's a bit. Here's a bit in the register, 1 bit. Bit 0 is timer 1 flag, okay? You don't have to care about like why this guy is in this register. You just need to know this one will be set. Set means it will be put a 1 in it once timer 1 overflows. It will be automatically got a 1 in here, so I have to manually clear it before that if statement or while loop. I'm going to show you that in the code. But now you know that this one will become 1 once timer 1 overflows. Okay, similar questions will be in the exams in the future. Okay, super fundamental. Now you get down here to the bottom. You see TMR1 interrupt flag. Okay, if it's getting a 1 there, which means it overflowed, right? If it's a 0, which means it didn't overflow. So you can use this one as a condition in your if statement. How do you want to write it in the code? Like if PIR1 bits, right? That's how the compiler tells you to do bits. So if you put a bits here, you are telling the compiler you are trying to get access to the bits into the register. So dot. So you're accessing that register, a certain bit in the register. Which bit? What do I want to write after that?
TMR1 interrupt flag.
Yes. TMR1 IF. If this is what? I'm going to do the job. Or let's say while. Doesn't matter, I think. Doesn't matter. You want to hold it there, so it should be a while actually. Yeah, 0. So flag's off, which means no overflow. It's still counting. Still doing the job. So counter is still within that range, right? Still doing its job in here. Still doing it. Reaches here, so this will become 1. It's gonna jump out from the while loop and do whatever after, okay? So in that case, after this while loop, this becomes 1, okay? So you can never get into this anymore because this is 1. And this condition requires a 0. What you want to do before it? Before it, what you want to do? Reset it, right? How do you want to reset it? How do we reset it? PIR1 bits dot TMR1IF. Yeah? Why?
Because we're resetting it back to 0.
Yeah, so it is able to get into the while loop. Otherwise, you can never get back to it. So do this first on the top, or right before this while loop, so you can get into it.
You have to reset the timer too to get back to 0.
No, it overflows, it becomes 0, all zeros.
Oh, okay.
It carries out, and that one will go nowhere. Any questions on this? No questions?
So when it sets the interrupt flag, you want it stops counting?
No. If you don't stop the timer, it will keep counting. Because it's going to come back. Will come back to the top if you have a loop, right? It's going to come back, so it's going to clear the flags and get into it and start counting again. Depending on your code, you can control everything really well, actually. Okay, let's take a look at more examples, so you'll get to know all these different examples and techniques. So now let's try this one. Timer 0. Timer 0. So the flag bit in flag bit of timer 0 is in a different register, different name. What is that one? Int count, interrupt count. So still want to see this page, okay? Still want to find this page, because you see it's over here. It's not even at bit 0. It's bit 2, 0, 1, 2, right? It's bit 2. Timer 0 flag. Timer 0 flag is bit 2 here, right? Same description, same thing for timer 0. Very similar way to operate it, to be operated. Okay, that's why in the code you have to use this register. Put a 0 here, right? Okay, and put a 0 here. So we're manually clearing these flags. Okay, so when you are writing into the timer, all right. So timer 0 writer. If it's timer 1, it's gonna be timer 1 writer. Write timer. Sorry. Timer 0 write timer. You start writing a count to the timer. So what's happening is that number is being split into 2 bytes and being assigned to these 2 registers. Take a quick look at it. I'm gonna jump into the paper to show the concept over here. Are you getting this? So this argument is a count, number of counts. Remember what we put into the counters, into the timers? What are these numbers? Counts, right? They are just counts. So that's why when you are writing to the timer, you put counts in there. So how do you put the counts into it? So this one, you still have to take a look at the function, the details of the function, what it does to it. So the counts you got from the calculation is the count that you desire. However, it starts from a certain point, right? Like this. This is your desired counts. Okay? However, what you put into the timer is a number starting from 0. Is this number. That's 0, 0x, 0, 0, 0, 0. So for the timer 0 write timer function, this number should be what?
0 minus the desired counts.
Because whatever you're putting here, for example, 5. Just give an example. 5. So 5 will be put into here. 5, starting from 0. So it's going to put a 5 in here. Okay? So if you start a timer, I might getting a 5 counts for my timer to overflow. Is the timer going to overflow after 5, after the 5th counts?
No.
You need a what?
16.
You need a this, right? You need a this, not this. Is that clear?
Yeah.
So how to get this?
2 to the 16.
2 to 16 is minus 5. So whatever you want to put in here, should be 0x100000, 4 zeros, which is 16 zeros in the hex number, minus your desired counts, right? So the conclusion here is you are not directly putting your desired counts into the timer writer function. Instead, you have a 2 to the 16th minus that desired counts. So it's going to start from the point and finish the counts to serve your goal. Right? Is that clear? 2 major questions. Given the time to calculate for the counts, give the counts to calculate the time. Any other questions for this type of questions?
So when you write in your counts, right, you can start it and it'll get you the desired amount of time where it plays the note, right? How do you write in a frequency to the timer? Like you can tell it like this is how long you can play by doing this.
Yeah. So what's happening? Yeah, good question. Very good question. So let's do that as the next example here. So what's happening is you can do similar techniques in your code. For example, like while, right? While this PIR1 bits dot timer 1 IF, right? Whenever this is 0, you do the job, right? And whenever it's 1, it jumps out from it. So then you have A port, for example, RA0. Another question can be in the exams. Latch is for output. Port is for input. Port A, port B, port C, that's input. That's an input buffer. Latch is output. Trace is direction. Is that clear? Okay. So latch is output, right? So you are giving. Okay? You toggle it. Okay? So which means, for example, this count of the timer we put into it gives you 2 milliseconds time frame for the counts. So what that means is, so for example, you have an offset here, right? And this is all the counts, number of counts, and we already learned if you counts are given, you can calculate for the time, right? How? Counts divided by 60 mega, okay? Can we do that? Yes. We can definitely find out that, no problem. So we set up timer 0, timer, whatever, just one timer, okay, just assume. So this number of counts will do a 2 milliseconds. It's a hold here for 2 milliseconds, then jump out and toggle it. So what's happening is you have 2 milliseconds, then toggle, 2 milliseconds, then toggle, 2 milliseconds, then toggle, okay? So you are getting a certain frequency.
That makes sense. Okay.
So are you using a timer? So basically for the music example in the lab, these are called pitches, right? Pitch. Every pitch of the keyboard. I'm going to show you that keyboard really quick, even though I don't have a musical background. But my dream is to be a pianist anyway, just to let you guys know. What? I'm going to retire in 10 years, and I will start learning piano.
Start learning.
And become a pianist in 2 years, hopefully. Anyway, Okay, that's a good time to learn it now. Thanks to this class. C, D, E, F, G, A, B, right? C, D, E, F, G, A, B, every octave. So do, the first do here is marked as a black. Do, re, mi, fa, sol, right? So do is C, C, D, E, F, G, A, B. And then starts another octave. C, D, E, F, G, A, B. Okay? Same cycles, but different pitch. So this is definitely higher octave, lower octave. And the black keys are half step. Is that a good term to use? It's a half step, not a full step. Thank you. So C sharp is half step from here to here. Okay. D sharp is half step from here to here. So it's full, half. Full. You know what I mean? Because C to D is a full step. In the middle, you got a half. But from E to F, there's no black key. So which means from E to F, it's only a half step. Okay? So C, D, E, F, G, A, B is one cycle, one octave. However, this brings us to another problem. Nested problems. We probably don't have the time to run the quiz today. We'll do it next week. It's okay, I already finished all the important materials. Already attracted enough attention from you guys. You already learned.
Yeah.
You got tricked. Next time it's gonna be the true quiz, okay? Next week. Anyway. So he brought up the good point. I think whatever on the website might be wrong. Might be wrong. I'm not I don't have a musical background. You guys let me know, okay, if this is wrong. It's the same thing here, the same table. Let's start from this C, okay? C. C, D, E, F, G, A, B. They're all 4, number 4 here. But why the previous A, B, the previous octave, has also 4 here? You know what I mean? You see, it's a fourth, hopefully it's a 4th octave. So for these ones, starting from C, right? C, C sharp, D, D sharp, E, F, G, A, B. And you are done with octave 4, the 4th octave. Hopefully I'm using the correct term. However, you have 4s, you have 5s. I think they should all be 4s.
A does indicate the beginning of an octave.
Really? Good to know. Okay, now let's start from here. A, B, C, D, E, F, G. And that becomes correct. A, B, C, D, E, F, G. That's correct. A, B, C, D. Okay, they're all correct. That's good. So in that case, whatever here are correct as well. Okay, that makes sense. Let's jump back to not the keyboard, I hate it. This one. So what's happening is, so we are going to put all the scale, are basically the counts you find from the spreadsheet. Right, you do the calculation, you drag it, you find all these number of counts, and what's really happening for the timer is for the half cycle. So for example, one scale has a certain frequency like this. It could be, for example, it's a C4, okay? C4. All right. So we are using the timer to create a certain frequency. Why do we want to use a timer, not like using something else, just to estimate?
So the board can do other stuff. Use the timer.
It could be one of the reasons. But timer is very accurate, right? Is it accurate? Yes, it is. It is super accurate. So if you are using a very accurate timer, we are creating a really accurate tone over there, or scale. Should I use scale or tone? Scale. Okay? So it sounds right. If you put all the scales together, it sounds like that song, right? Not something else. So it's important to make it accurate. So for this type of frequency, it's just a 50% duty cycle because it's just toggling with the same amount of time. It toggles, then it toggles again. So what's really happening is for every time frame over here, what is happening for the timer, okay? You have an offset. So during that time frame, what's happening?
Speakers off.
It counts, right? It counts really hard. That's what's happening.
Yeah.
Okay? And you can manipulate that number of counts to create a different time frame for every half cycle of that scale. To create a different scale. Okay, if you come back to the code, oh, that's a code you guys can use, right? But I have a lot of empty areas to let you fill up. So for example, here you got a counts. It's a certain song, so that's a song, right? It's a song. The song has every single scale in every single note in here, and every single note has a certain scale, which is implemented by the count number of counts. Does that make sense? So the count you put in the timer will give you a certain time delay to create that little pulse to make it sound like that scale. Okay? So you have to put the whole song's scale into this curly bracket, but not necessarily all the whole song scales into this curly bracket. And I'll let you guys think about why. The reason is you pick up one note, you use a loop to loop through the whole thing here, every single note for the song. You pick it up, okay? And then you every single note here has a number on the top. You define it, and that number represents it's an index in a scale curly bracket in the scales list. That makes sense? One song can have repeated scales, right?
Are we allowed to change how long a quarter and a half note is if our song is like faster or slower than the standard?
Sure.
Okay.
Yeah, that's gonna be the time delay in between different notes, right? So now the notes, the delay between notes is like, for example, twinkle, twinkle, right? So I'm now doing twinkle, twinkle, so it's twinkle, right? So there's a time delay. Twinkle, twinkle, little star, right? So twinkle, and the time delay is controlled by timer 0.
The only thing about your scale is that you had a scale of 6, right? So is that just specific to like your code because you only had 6
Yeah,
notes?
yeah.
So like if I have like 12 different notes, I would need to make that array size 12.
Yes,
and
yes. I have to cover all the scales in the
Gotcha.
notes.
Colston said something about you have to have at least 2 octaves.
Yeah, then just change it according to the instructions on the lab. The lab instructions, okay? Any questions before we go? No? Have a good weekend.
Thank you, Professor.
Sure.
Do we have a class on Wednesday?
Nope. It's
Is it for your
lab next. Oh yes, lab 4 on Thursday, right?
Like, just see if I'm doing kind of on the right track with my homework.
Sure. Yeah, we can do it outside. There's probably possible. Let's see outside.